Okay, so this is our second video for chapter 4, and in the first video we were working on example 4.3. What we're trying to do is we are trying to do a quick recap, find out the force required to bring this car to a stop. It's traveling at 100 kilometers per hour, and we want it to stop to a velocity of 0 within 55 meters. So force, if we remember Newton's second law of motion, force is equal to mass times acceleration, and we know the mass. So if we can find the acceleration, we will know the force. So we need to find out the acceleration of this vehicle from its current velocity to its final velocity. And we looked at our constant acceleration equations and chose this one so that we can find acceleration, because we know the final velocity, we know the initial velocity, and we know the difference in position, x minus x naught. So we're starting to plug into this formula until I realize that the velocity given is in kilometers per hour, and those are not the units we want. We want meters per second. So we're going to have to take a step back here and convert our 100 kilometers per hour into meters per second. And we do that by getting rid of kilometers by putting it on the bottom. So for every 1 kilometer, there are 1,000 meters. So now the kilometers will cancel out. So that gives us meters per hour. So we need to convert the hour. For every 1 hour, there are 3,600 seconds. And so now our hours will cancel out. And we end up with 100 times 1,000 divided by 3,600. 27.8 meters per second. So I'm going to come over here and just going to erase that and replace it with the initial velocity of 27.8 meters per second squared plus 2 times the acceleration times x minus x naught is 55 meters. So now I just need to solve this equation for acceleration. So I think I've got enough room here. Acceleration is going to be equal to, I'll need to move this to the other side, so that becomes negative 27.8 meters per second squared. And make sure that negative is on the outside, because we want this to be negative after we square it. We would have squared it first and then moved it over. And divide by 2 times 55 meters. Okay, and that should be negative 7.0 meters per second squared. So there's our acceleration. It is decelerating. The car is traveling initially to the right, so that's positive velocity. In order to stop it, we need to accelerate it in the opposite direction, so that's a negative acceleration. That's what the negative sign indicates there. So now we just need to find the force. Force is equal to mass times acceleration. And so our force is going to be our mass, which was, let me jump back a slide here, 1,500 kilograms. 1,500 kilograms times our acceleration of negative 7.0 meters per second squared. And so I really used up all my room on this slide, didn't I? So the force is 10,500. A kilogram meter per second squared is a newton. So that is the force. 10,500 newtons will be required to bring this car to a stop within 55 meters. All right, let's move on to Newton's third law of motion. And this is whenever one object exerts a force on the second object, the second exerts an equal force in the opposite direction on the first. So you've probably heard this before, something like, for every action, there is an equal and opposite reaction. So, for instance, the hand pressing against the edge of the desk. When the hand presses against the desk pushes back against the hand. Or here, this ice skater is holding on to the wall. If she pushes against the wall pushes back on her. And it is important to note that the forces are being exerted on different objects. So there's the force of the skater on the wall and the force of the wall on the skater. So not both forces are not being applied to the wall, for instance, and both forces are not being applied to the skater. One is from the skater to the wall, and the other is from the wall to the skater. An interesting misconception about rockets taking off is that when a rocket takes off, that its exhaust is pushing against the ground, which is what is launching it into the air. And that is not true. The ground doesn't need to be there. The rocket is not pushing against the ground. What is causing the rocket to take off is just simply the fact that you have all this hot rocket fuel gas, this exhaust pushing out in this direction. So that causes a force equal and opposite, which causes the rocket to take off. Rockets like this could work in outer space where there is nothing, where there's a vacuum. This phenomenon can also be demonstrated if you are on a boat in a pond and you throw something heavy, like a cinder block, off the back end of it. If you throw that heavy object off the back of the boat will go forward. The textbook points out here that it likes to use this type of annotation to denote what force is being talked about. So, for instance, here they use the subscripts GP or PG for this particular example. So we have this lady walking along with her feet pushing against the ground, and the ground pushes back against the person. So for the force exerted on the ground by the person, it uses the subscript GP. So this is the force on the ground. And this is the force by. So G and P are only used for this example because we're talking about a ground and a person. We could use any letters here to denote any two things, like when we had the image of the skater holding onto the wall. We could say the force on the wall by the skater, or the force on the skater by the wall. So it's just a way of showing what object the force is being applied to and what object is applying that force. And this is a way of just saying that they are equal and opposite. They are equal, but with an opposite sign. So if a force is a push or a pull, it can really be exerted by anything. All sorts of objects or machines or people can be the sources of a force. But one of the most common forces that we deal with in this class, and I suppose in the world generally, is the force of gravity. So if force is equal to mass times acceleration, and we're specifically talking about weight, which is the force caused by gravity, we can substitute the generic A, which could be any kind of acceleration, with G. A little g, with the arrow over it indicating that it is a vector. Little g is the acceleration due to gravity, which is 9.80 meters per second squared. So this is really just still Newton's second law of motion, F equals ma, just in a very specific context, which is changing that a to a g. So this is the force due to gravity, also known as weight, is mg. So if gravity is the force that pulls things down, the equal and opposite force that pushes back against it is called the normal force. So we've got F sub n for normal. Normal in this case means perpendicular. So it is the force that is perpendicular to this tabletop, to this surface, pushing back against whatever object is sitting on top of it. So here we have this bust of Abraham Lincoln sitting on top of a table. It has a certain weight, a force due to gravity pushing down. Something has to be pushing back against it, otherwise there would be an imbalance of forces. And wherever there is an imbalance of force, because force equals mass times acceleration, then the object would be accelerating. There would be some non-zero acceleration here if the sum of forces was not zero. So that means that this would be basically breaking the table, falling, and accelerating in the absence of this normal force. So there is a normal force that's pushing back, equal and opposite to the weight pushing down, in order to keep this at rest. So we'll talk more about that later. We'll do a chapter involving static equilibrium. But for now, we just need to be familiar with this F sub n, the normal force. Okay, so what happens, let's look at this example, what happens when a person pulls upward on a 98 Newton box with a force of 100 newtons? Okay, so this is a very simple example, but it really kind of makes us think a little bit more scientifically about what's going on here. So gravity is pulling this box down with a force. That force is equal to mg. And we are told in the problem statement that the weight of the box is 98.0 newtons. So that's how the force gravity is pulling it down, and we are pulling up on the rope with a force of 100 newtons. It's like a tug of war, except it's not perfectly balanced. We're pulling up with a force greater than the weight is down. So the net result is this box is going to accelerate up. It's going to accelerate up. The imbalance, the sum of forces, is 100 up and 98 down. So it's 2 newtons. And it looks like I'm going to have to hold that thought right there and pick up the rest of this in the next video.